We've been looking at quantifiers, we've been looking at negation. Now let's look at both of them together. So suppose I have a statement like this: all first year maths is easy. That involves a quantifier. All first year maths is easy. Supposing you don't agree with that, and you want to express the negation of that. Well, we can say that very simply, just by saying not all first year maths is easy. However, what I want to look at is that we can simplify that. If you're saying not all first year maths is easy, can you say that without actually using the word not? Well, you're not saying that all first year maths is hard. You're saying not all of it easy. In other words, some of it is hard. So some first year maths is hard. Another example. Suppose I have an existence statement. There exists an x in the set of real numbers such that x squared equals -1. Suppose I tell you that. You know I'm wrong, and therefore you want to tell me that I'm wrong, and just putting it simply, you can say there does not exist x in R such that x squared equals -1. But again, we can simplify that so that we don't actually have to use the word not or the phrase there does not exist, because this is saying that if you take any real number in x, any real number x, and square it, we're saying you will never get -1. In other words, for all x in R, x squared is not equal to -1. Now those two examples illustrate the following. If I have an all statement or a universal statement for all x in U something or other, the dots just represent some statement, then the negation of that is to say that for some x in U, the statement is false. In other words, for some x in U, not whatever that statement might have been. Likewise, if I have a sum statement, for some x in U, some property holds. Again, the dots are just a property. I don't care what they are. If I'm saying that's false, I'm saying that for every x, the property fails to hold. More formally, for all x in the universal set, not whatever that property might be. So therefore, if I want to disprove an all statement, in other words, I want to prove it's false, in other words, I want to prove its negation, we have to prove a sum statement, because the negation of this is a sum statement. You might have noticed we've seen that before. To disprove an all statement, we provide one example, often referred to as a counterexample, to prove an existence statement. We also can do it, not always, but we can do it by giving one example. You might have noticed that was the same thing. Why is it that we disprove an all statement in the same way that we prove a sum statement? Well, because they really are the same kind of statement. The negation of an all statement is a sum statement. We can prove that the all statement is false by giving an example where it doesn't work, often referred to as a counterexample. The counter in that, well, strictly speaking, it's irrelevant. It's just an example which is being used for a particular purpose. Nevertheless, the word counterexample is quite common. Similarly, suppose you've got to a sum statement and we want to prove that it's false. Then we can prove an all statement. Now, in principle, you can just prove that as an all statement. So if I want to prove this statement, let x be an element of U, prove that not ... whatever that statement might be. In practice, however, you might well find that it's easy to prove the sum statement false directly. So assume it's true and use proof by contradiction rather than looking at the all statement instead. And let me give you an example of that. Suppose I have the statement square root of 2 is rational. Now that's a sum statement because it says square root of 2 equals m over n for some mn in the set of integers. The negation of that statement, so if I decide that's not true, I want to prove the negation, is the square root of 2 is not an element of Q, and that means for all m and n in Z, square root of 2 is not equal to m over n. And if you think about it a little bit, I think it's fairly plausible that doing it that way would be very hard. Because you'd have to say let m be an element of Z. Anything at all, we don't know specifically what it is. N, likewise, we have to prove in all cases an inequality square root of 2 is not equal to m over n. Whereas, probably much easier to start here, hypothetically assume that that is true. We've got an equation then to work with. That's much easier because we can do lots of things with equations. And hopefully we can eventually reach a contradiction which shows that our assumption is false and therefore the square root of 2 is not in Q. Indeed, as you know, we can do that because that's exactly what we did in a proof recently. Here's another example. Prove or disprove the following statement. No prime is congruent to 14 modulo 25. Now, how could we do that? Well, I think for a start, it's not entirely clear what the logic is, so let's try and rewrite that. If I'm saying that no prime is congruent to 14 mod 25, that's the same thing as saying every prime is not congruent to 14 mod 25. In other words, this. It's an or statement. For all primes p, we have p not congruent to 14 mod 25. That turns out to be false. How could we know that? Well, it doesn't seem to be very clear how we could try and prove anything like this. So if all else fails, we could just look at some examples. We could look at primes p, say 2, 3, 5, 7. Well, that's not congruent to 14 mod 25. If you divide by 25, of course, you get a remainder of 2, not 14, and 3, not 14, and 5, and 7, not 14. And you'd have to keep on going for a while. You might realize that this would be easier if we use the contrapositive. So that means that if p is congruent to 14 mod 25, then p is not prime. Why is that better to do it this way? Well, very simply, because there aren't so many numbers congruent to 14 mod 25. There is, in fact, exactly 1 every 25 that's congruent to 14 mod 25. So there are fewer things to look at. As you can see the primes here, we haven't even got to 14 once. We've already got 4 primes. And there's going to be 2 more before we get to 14. So maybe this would be easier. So if p is congruent to 14 mod 25, then I want to ask whether it's prime necessarily or not. Well, 14 is not. Now that, if you think carefully about the logic, does not answer the question, because that says if p is congruent to 14 mod 25, then p might be not prime. It doesn't say it's definitely not prime. So that's not conclusive so far. The next one we look at, 14 mod 25, is going to be 39. That's not prime. So it still doesn't answer the question. May as well try a bit more. We'll have 64. Well, that's definitely not prime. Next one's going to be 89. And now, if you think about it a little bit, that is prime. What do we have here? We have a counterexample. If p is congruent to 14 mod 25, then p is not prime. To prove that's false, we need an example of p, which is congruent to 14 mod 25, which is prime, and that's exactly what we've got, 89. And that's why the statement is false. So it's an or statement for all primes p. P is not congruent to 14 mod 25, and to disprove it, we prove the negation. The negation of that is there exists a prime p, which is congruent to 14 mod 25. And to prove an existence statement like that, or to disprove an all statement, what we need is just one example. And so here's the proof. 89 is a prime, and since 89 is 3 by 25 plus 14, we have 89 is congruent to 14 mod 25. In other words, we've given an example, p equals 89, which is prime, and p is congruent to 14 mod 25. We've therefore proved this existence statement is true. We've proved, therefore, this for all statement is false. And that's our answer. The statement is false. A couple of comments about this. Firstly, one that I haven't actually written down. Writing the proof. As I've said before, you should write a proof with the reader in mind so that the argument is comprehensible to the reader. If you wanted to write this at a more advanced level, if you have confidence that your reader can do routine calculations for themselves, it would be quite common just to write this the following way. I'll say this statement is false, proof 89 is a counterexample. And I could finish there. If I'm confident that my reader has the understanding of what that means, that it means that 89 is prime and it's congruent to 14 mod 25, and that if I'm also confident my reader has the necessary arithmetical ability to check those facts, that 89 is prime and that it's congruent to 14 mod 25, then I might just write down for my proof 89 is a counterexample. If you're not sure, then give some more explanation. As I've mentioned before, if in doubt whether to give more explanation or less, you should nearly always give more. Some other things to learn from this proof. It's not obvious whether the statement is true or false, so this statement I gave you at the beginning, no prime is congruent to 14 mod 25, or to put it in a slightly clearer way, for all primes p, we have p not congruent to 14 mod 25. It's not obvious. There's no obvious way of working backwards. So we could try a few examples that might give us a counterexample, as it did in this case. Or it might suggest a pattern which could be used to prove the statement true. I'll give you an example of the latter. Here's another statement. Consider the following. I'm going to say, is this true or false? Prove it. So prove or disprove the following. There exist two consecutive triangular numbers whose sum is prime. Well, again, there doesn't seem to be any obvious counterexample. There doesn't seem to be any obvious way of working backwards. So let's just try some examples. In case you don't know what triangular numbers are, they are the following: 1, 3, 6, 10, etc. And where that comes from is that's 1 plus 2, that's 1 plus 2 plus 3, that's 1 plus 2 plus 3 plus 4, and so on. And the reason they're called triangular numbers is that you can do triangles of dots. That's 1 plus 2, that's 1 plus 2 plus 3, that's 1 plus 2 plus 3 plus 4, and so on. This is why they're called triangular numbers. So, there exist two triangular numbers, two consecutive triangular numbers, whose sum is prime. Well, let's just try some examples. 1 plus 3 equals 4. Well, that's not prime. 3 plus 6 equals 9. That's not prime. 6 plus 10 equals 16. That's not prime. So we haven't yet found an example to prove this is true. Remember, it is an existence statement. So to prove it's true, I just need one example. I need to find two consecutive triangular numbers whose sum is prime. I haven't found an example so far. What do you think? Should I keep looking for further examples in the hope that I will find an example, two consecutive triangular numbers whose sum is prime? Or do you think you can see something in these results which gives you a hint for why it might never be true and that this statement is in fact false? I'll leave that one up to you to think about entirely. I won't give you an answer to that one. Let's now go a bit further with this. And we've looked at quantifiers, we've looked at negation, we've combined the two of those, negation of quantifiers. We've also looked at multiple quantifiers, and I'm going to combine those even further, and we're going to look at negation of multiple quantifiers. We know that the negation of an all statement is a sum statement. We know that the negation of a sum statement is an all statement. And so we can use these ideas to simplify further and further the negations of statements involving multiple quantifiers. So for example, suppose I have this statement here. For all x, for all y, there exists z such that whatever. Again, the dots are just some statement there. Simplify the negation of that. Well, the negation is very easy to write down. You just put a negation symbol in front of it. But we can scarcely say that's simplified. Remember also something I mentioned before. Don't use the symbolic stuff, please, too much in writing down your proofs. When you're doing things like this, which are kind of algebra and just shuffling symbols around, that's when it's a good thing to use symbolic notation. So I can use that. Now, what's this statement? Well, let's just look at it one step at a time. It's for all x, something. For all x, something is true. The negation of that is there exists x such that the following is false. Like so. I can now keep going though. I can simplify that even further, because this statement here, I'm saying not for all y something is true. The negation is there exists y such that this something is false. And that's what I've done here. There exists x. I've simplified that as much as it'll go. I'm not considering that anymore. I'm now just saying that if it's not true that for all y this is the case, then it must be true that for some y this is not the case. And finally, I can simplify one step further. If it's not true that there exists z for which ... is true, then it must be that for all z ... is false. And we have something like that as our final simplification. Example of this. And once again, I'm going to do a calculus example. I'm going to say that a set S, a subset of the real numbers, is called open under the following circumstances. And I've put this deliberately, I've put this statement in symbols, which among other things I hope will convince you that it's not good to use symbols too much, because we're going to have to do quite a bit of work to decipher what this actually means and try and work out what it's saying. And I want to ask the question as to whether a certain particular set is open or not. The idea is that a set is open if it contains no part of its boundary. We can make that more precise in more advanced work, but let's just draw some pictures and see if we can work out what this means. And the example I'm going to ask is the following. Is the set of numbers from 1 to 2, where 1 is included and 2 is not, is that open? And as always, of course, prove your answer. Well, let's see what we can do. Since we've got a question about sets, which are subsets of real numbers, a good thing to do is to draw a number line. So I'll draw my number line. I'll always put 0 on for a reference point. And the set I'm talking about is from 1 to 2. Let me draw it this way to indicate that my set is the one here in red, where 1 is included and 2 is not. I hope you're familiar with the convention in calculus. We'll draw a filled-in dot if the number is included. So 1 is included. The square bracket here indicates that 1 is included. And we'll draw a round dot, or in the notation, an empty dot, or in notation a round bracket, to indicate the number is not included. So is that open? Prove your answer. Well, here's the definition. Let's for a start imagine that we're going to try and prove that it is true, that it's open. So for all x in S, so I'll take an x in S, this red set is my S. I'll draw my numbers on the number line here. Let's take an x here. I'm going to say there exists an epsilon greater than 0, such that for all y in R, if the absolute value of x minus y is less than epsilon, then y is in S. So what am I going to do here? I'm going to look at y values which are within epsilon each side of x. So let's say I take that distance there to be my epsilon. So that's going to be x minus epsilon. And going the other side, say about there, is going to be x plus epsilon. Okay. So I've got my x, I've got my epsilon, and I'm saying that for all y's in between here and here, all y values are in the set S. In other words, all y values there are within the red set. Is that true? I hope it's clear that it's not. Because I could take a y here, that's within the bounds I set, yet it's not within the red set. Okay, so far so good. Does that prove the statement? Well, it doesn't, because if you think about it, let's just look at this epsilon here. The statement is that there exists an epsilon which will make the following work. Now, I chose one here which didn't make the following statement work. Now, is that conclusive? Well, no, it's not, because I've chosen an example which doesn't work. The statement is merely saying that there is an example which does work. Let me draw the diagram again. So here's my set S, once again, same as before. That's 0, that's 1, that's 2. Here's my x. Remember, although this epsilon didn't work, I'm just saying that there is an epsilon which does work. And I hope you can see there is. Say, for example, I took epsilon to be that big only. Then there's an interval each side of x to a distance epsilon. That one there is x minus epsilon. This one here is x plus epsilon. And now my claim is that for that choice of epsilon, any y in between here is within the interval 1 to 2. In other words, is within the red set. And that's clear. I hope that's clearly true. Any y here is within the red set here. So in this case it works. So I've shown there is an epsilon greater than 0, such that for all y in R, if this is true, which means y is between x minus epsilon and x plus epsilon, then y is in S. That's true. Does that make the whole statement true? Well, it still doesn't. Because I said this was supposed to happen for all values of x. I've proved this works for one value of x only. But the statement says it's supposed to work for all values of x. Let me draw another diagram. Once again, here's our set S, going from 1, which is included, to 2, which is not. So if I choose my x here, then I can find the epsilon. It works. If I can choose it here, I think it's fairly clear that I could do something similar. Here can be my x minus epsilon and x plus epsilon there. Any y's within that are within the red set. Is there any x within this red set for which this would not work? If you think about it a little bit, you might see, yes, there is. If I take x to be right here, x equals 1. Remember, 1 is a part of this set. This notation here means that 1 is included, although 2 isn't. So I couldn't take x equals 2, even if I wanted to, because that's not in the set. Notice carefully what the statement says. For all x in the set S, x can't be just any old real number. It has to be an element of the set S, which is the set in red in these diagrams. And if I take x equals 1, which is an element of that set, can I now find an epsilon? Well, no, I can't, because no matter how small I make that epsilon, the x minus epsilon is going to stick out below 1, and a y in this set between x minus epsilon and x plus epsilon might not be in S. And therefore, the answer is that the statement is false. So 1, 2 is not open. Let's see how we prove that. Well, to prove that, here is the definition of S being open. If we want to prove it's not open, we have to prove the negation of that. And from what we've done already, we can write down the negation of this and simplify it. So I'll ask you, actually, for an exercise for yourself. Just pause the video, write down the negation of that. So just put a negation sign in front of that, and then simplify all the way along, step by step, as we did earlier. Here's what we have to prove. I have to prove that there exists a set, an element x in S, where S in this case is the interval from 1 to 2, such that for all epsilon greater than 0, there exists a y in the set of real numbers, such that this statement is false. Now, how can an if-then statement be false? Well, if A then B, the only way that can be false is if A is true and B is false. In other words, x minus y is less than epsilon, and y is not in the set. Again, reminding you the set S in this case is the interval from 1 to 2. So, let's prove that in the usual way. And in fact, before we write anything more, before I reveal what I've written, let's use some logic. Like I said before, if you've got lots of logic, then it's a good thing to write down the logic first. My first thing is I have to choose an x in the interval 1 to 2. Choose x equals something. Then I have to let epsilon be any positive number. Let epsilon be greater than 0. I have to choose a value of y in R, and then I have to prove that the absolute value of x minus y, I have to put in some proof here to show that it's less than epsilon, and I have to show that y, giving some reasons, is not in the interval 1 to 2. So notice once again, as I suggested before, often a very good thing to do, write down the logic first. Now writing that down, together with looking at the diagrams we saw earlier, hopefully it makes it clear what we should do. Here was our final diagram. And that reveals, I think, that the value of x we need is going to be 1. So I'm going to say choose x equals 1. That's what I've done here. I have to say let epsilon be greater than 0. Remember, I'm not choosing the value of epsilon because I have to prove something for all positive values of epsilon. Then we have to have a value of y, which is in R, and I want that y to be one which is not in the interval from 1 to 2. Where would that be? If you look at the diagram, look at this one here. I've got my epsilon. It could be anything. I've drawn a specific one here as a representative diagram, but it could be anything. How can I find a y which is somewhere in here? In other words, it is between x minus epsilon and x plus epsilon, but it is not in S, which is the red set there. Well, it's just got to be 1 minus a little bit. Y would be there. What could that be? It's got to be below 1, so 1 minus something. It can't go down as 1 minus epsilon, can't go down that far, because that's too far. That takes it outside this curly bracket, this round bracket here. So if I do perhaps 1 minus a half epsilon, that would do it. And I think I can reveal the rest of the proof now. I'm going to choose y equals 1 minus a half epsilon. Now, what do I know about that? X minus y, absolute value. I have to prove it's less than epsilon. Well, x minus y, here's x, here's y. Very easy to see that x minus y is a half epsilon. The absolute value of that is also a half epsilon. It's definitely less than epsilon. So that's proved, and I have to prove that y is not an element of the interval 1, 2. Well, the interval 1, 2 starts at 1 and goes upwards, but y is less than 1, and therefore y is not in the interval from 1 to 2. And finally, some things that we can learn from this proof. It may be helpful to draw pictures to assist your intuition, particularly something like this. That's a very complicated statement. Again, as I said before, I hope this will convince you, among other things, of the value of putting things clearly in words. Putting things all together in symbols like that really does make it, often, unnecessarily complicated. As I said before, good thing for just messing around with the symbols, good thing for writing down the negation here. That was great. But for actually understanding what it means, not so good at all. Pictures might help. The negation of an if-then statement, if A then B, can be expressed A and not B. Because this is saying that if A is true, then B has to be true. If I'm denying that, I'm saying there's a possibility that A is true and B is not true. So A and not B. Finally, notice that the first 3 lines of our proof here deal with the 3 quantifiers in the statement. Our statement says, this is what I'm proving, there exists x in the interval 1 to 2, so I choose a suitable value. Following on, for all epsilon greater than 0, so I let epsilon be an unspecified positive value. There exists y in R, so I choose a y, which is certainly a real number, such that these 2 things are true. So I check them individually. I check that x minus y, absolute value, is less than epsilon, and I check that y is not in the set 1 to 2.